Thank you for that very interesting presentation. Our next presenter is unable to be with us in person today because of some extenuating circumstances, but it is my pleasure to introduce Reid Van Lehn. Reid is the Hunt-Hougen Associate Professor in the Department of Chemical and Biological Engineering at the University of Wisconsin-Madison. He earned his Ph.D. in Material Science and Engineering from MIT and joined UW-Madison in 2016, where his research group uses molecular simulations and data-centric methods to characterize, predict, and engineer the behavior of synthetic and biological materials for applications relevant to human health. And today he'll be presenting polymer recycling and contaminant removal from multi-layer plastic packaging by solvent-targeted recovery and precipitation.
Well, first things first, following that last excellent talk, I will say that I am a professor of chemical engineering. I'm literally teaching on fugacity tomorrow. These are my notes. So Jennifer, if you do have time later, I can give you a quiz. I'd be happy to do that if you stick around. So thank you all very much for inviting me to speak today. I do want to apologize for not being there in person. We did have some family medical issues that necessitated me being here. But I'm very excited to follow from those last two talks. I think they brought up a lot of issues that I'm also excited to talk about in the context of some of the work that we're doing here at UW-Madison, as well as at Iowa State University, as part of a center called the Center for the Chemical Upcycling of Waste Plastics. So I'll start by telling you a little bit about this center. We are a multi-institute center, as I mentioned, Wisconsin, Iowa State, as well as UMass Amherst. We're also partnering with a number of national labs, most notably the National Renewable Energy Laboratory, and importantly, a large number of companies. We heard a little bit about the plastics value chain, I think 2 talks ago. We have companies from all across the value chain that provide input to us in terms of how we can make sure that our science and the recycling technologies that we're developing are really going to be valuable across the entire plastics value chain and have real-world impact. So just to give you a sense of that plastics value chain, this is sort of a schematic very similar to what I think Jennifer just showed, where we can imagine that we start from the extraction of natural gas and send it to steam crackers to produce new polymers to make our plastic material. And then we go all the way through synthesis, conversion, brand owners, retailers, consumers, and eventually to those materials recovery facilities that we heard about 2 talks ago. We're trying to develop technologies to put new recycling facilities where we would take materials coming out of a materials recovery facility and either take them into a form where they can be put directly back towards the plastic converters, or break them back down to those monomers, as we heard about in the last talk, and send them back through steam crackers in place of virgin feedstocks. So in other words, we're trying to divert material from the landfill and close the circular gap through this region here. Now, I'm going to introduce some terminology that I don't think I heard the other 2 speakers talk about, so let me just introduce it real briefly. I'm going to talk about 2 different kinds of waste. We're all familiar with what's typically called post-consumer waste. So this is the waste that we collect from our recycling bins. This is where we could deal with these with thermal pyrolysis that we just heard about in the previous talk. This is what's sent to mechanical recyclers. And a lot of the contaminants are introduced by consumers. There's another form of waste, which is called post-industrial waste. This is plastic that's often the byproduct of a manufacturing process. So for example, imagine I'm making like an oddly shaped yogurt container, but I'm trying to make that shape out of a plastic film that's rectangular. I'm going to have a lot of leftover material that is actually less contaminated because it's never gone out to consumers. It's also of known composition and is collected locally, typically by people like plastic converters. So we're going to focus on technologies that deal with this feedstock and that we're trying to adapt to deal with this feedstock, but both are going to be relevant to technologies we talk about. And just as a note, I mentioned pyrolysis. It was really nicely introduced in the last talk. We're developing pyrolysis-based approaches in the Center for Chemical Upcycling of Waste Plastics. We're also dealing with a technology called catalytic upgrading. So one of the outputs of pyrolysis is an oil. That oil can then be sent to be converted into other products, not necessarily just the monomers that one would use to make polymers. And this can increase some of the value of this pyrolysis oil, getting back to the economics that were asked in the question and answer process. I want to focus on a different technology, one that's fundamentally distinct, that we call STRAP, or Solvent-Targeted Recovery and Precipitation. This is ideal for materials that are coming out that are of high quality, meaning that they have specific properties that I'll talk about in just a couple of minutes. Now, what we're really interested in dealing with are materials like multi-layer plastic films. There was a really great question that asked about this that I just heard from the audience, but let me just introduce this class of materials for those who are less familiar. If I look at the breakdown of plastic usage, plastic packaging is about 40% of the usage of polymer resin. So it's a huge market segment. So that's where a lot of our material is going. And many of this plastic packaging material are what are called multi-layer films. This is a schematic of them at right. And the basic idea is that if I'm thinking about something like plastic material that I might use to wrap the meat that I find in the grocery store, it has to have a series of properties that can't necessarily be conveyed by a single polymer. So for example, I might need to reduce water and gas diffusion to maintain the quality of my meat, but I might need to have some level of mechanical rigidity or maybe optical transparency in order to show to the consumer what I'm seeing. So the way that this is introduced is by having a series of different polymers that are often in sort of molecular scale contact or adhesive contact. That also means I have to add layers, things like tie layers, which serve to basically glue these different polymers together. So this is extremely challenging because these are now multi-component materials, and they really cannot be sent in the vast majority of cases to mechanical recycling streams. So this is one of the reasons that Jennifer just said that many of our MRFs cannot take plastic packaging or plastic film, and much of this plastic manufactured material is just thrown out. So we really originally developed STRAP, and we thought about STRAP as an approach to deal with these type of materials. So let me explain the basic process to you. So this is a schematic of how we would deal with STRAP in sort of a real-world scenario. We would take plastic waste, like these multilayer films, and shred them down into really small amounts of material. Think about on the orders of 2 millimeter squares. Okay? These are then sent to what we call a strap line, where STRAP is a physical dissolution process. Okay, so let me explain what that means. If I look at this cycle that I'm showing here, imagine I take a multi-layer film that has, for the sake of example, 3 different polymer components, okay, red, green, and blue. Of course, many materials will have more than that. The idea of STRAP is to say, what if we choose a solvent that can selectively dissolve one of those polymer components, but not the others? So we're relying upon the thermodynamics of mixtures. We're relying upon the idea that certain solvents will have a chemical affinity for certain polymers that allow us to dissolve that polymer, but nothing else. So once I've dissolved off this red polymer into my selected solvent, I can filter away the residual green and blue ones. And then I can add in either what's called an anti-solvent, so a solvent that is a bad solvent for the polymer that's been dissolved, to trigger it to precipitate out of solution. Or I can imagine just cooling the entire system down, okay? I get back my red polymer as a solid, and I can do this sequentially. Now that I've got this green and blue one, I can further target a second one of those using a different solvent to separate them. So again, unlike the advanced recycling techniques or pyrolysis that we just heard about, there's no chemical transformation of the polymer here. This is more like a physical dissolution process, okay? So that's the basic idea. This allows us to separate polymers from a multi-component plastic product like a film, or in general, mixed plastic waste. So any plastic mixture in principle could be treated with this type of material. And the idea is that because we're not going back to monomer, if we do this right and we get a high quality plastic material out, it can immediately be reused for whatever the original application was without having to go back through the polymerization process. So our goal is to get a high quality food grade resin. And I think we talked about grading, or maybe we'll hear about this in terms of regulatory affairs a little bit later on, directly from this multi-layer packaging that can be reused as a feedstock to make the film again, okay? Now there are a series of challenges, of course, that we're dealing with. One of them is just the complexity of these films as well as other types of polymers. We've heard about additives, we've heard about contaminants in the last couple of talks. Many of them are what we call intentionally added, so things like color. We're also going to talk about non-intentionally added substances by the end of this talk. We have to choose solvents to dissolve these target polymers, and that's a thermodynamics challenge. How do we know what dissolves and what doesn't? And how do we also think about things like the cost of the solvent, safety, life cycle assessments, and all the different challenges that would arise from actually introducing this at a large scale. Contaminants and color will be a focus that we talk about a little bit later. Color is a really important one because remember, we're trying to go directly back to a product. So if we have an optically transparent material that comes out black, that's not going to be very reusable, right? And then finally, what we're thinking about right now is that, we are a scientific institution at a university, but how do we scale this up to be commercially relevant, and what kind of challenges do we deal with during that scale-up process? So let me give you a sense of the types of materials that we've been working with at UW. We're going to focus on these multi-layer films, many of which are what we call printed multi-layer films. So they have a brand logo on them that's introduced through an ink that's intentionally added, oftentimes between different layers of these multi-layer films. But we've dealt with a lot of other materials. So here's an optically transparent multi-layer film. This is what we call a rigid multi-layer film. So think about like when you buy toys for your kids that have that really rigid plastic packaging, this would be what it is. And we've shown that strap can convert this to the 3 original constituents that I'll show in just a couple of minutes. We've also dealt with some PVDC-based films. PVDC is interesting in this particular case because there are different types of polymers, some that can be dissolved and some that can't, that we call thermoplastic and thermoset. In this particular case, we can recover both thermoplastic and thermoset materials. Here's some other fun ones. These are what are called marine plastics. So here's the fun part of this job, is that every once in a while, people just mail us trash, okay, from all around the world. It's a very fun thing to tell PhD students, we're going to sort through trash and basically dissolve them in different substances. But here we got some really interesting trash from a research station run by NIST out in Hawaii. These are marine plastics collected by undergraduates, which we then tried to recycle using strap and remove a lot of the contaminants that accumulate during exposure to the ocean. And then finally, here's an example of polycarbonate that comes from eyeglass waste. A lot of the material that goes in your glasses ends up as that post-industrial waste that I talked about. Okay, so those are just some examples. We're going to focus now on this one multi-layer film. So this is this ink-based printed multi-layer film. So here's a rough schematic, and I'm going to show you some chemical structures here of the different components. This has 4 primary polymer components: polyethylene, which we heard about in the last talk; ethylene vinyl alcohol. This is often used as a barrier layer. We also have that polyethylene terephthalate. And then finally, we have an ink that causes the color. The ink has a binder that causes it to adhere to the other polymers. That's based on polyurethane. So we have 4 primary polymer components. We also have the color agent, so the pigment that gives rise to that orange color. We'll talk about that in a few minutes. All right, so here are the questions we have to think about. What solvents do we use to recover these components? In what order do we go in? What do we dissolve first? Once we recover these different polymers, what we call resins, can we actually reuse them in applications? And then what are the economics of this process, as well as the life cycle assessments? Coming back to a question that I think was asked of the last speaker. Okay, so I'll step through those in turn. So here's the only slide that actually deals with what my group really does, okay, which is computational modeling. I'm showing you a molecular dynamics simulation, which basically shows at nanometer length scales how polymers interact with specific solvents. So we use these types of simulations, along with a methodology called COSMO-RS, to calculate from first principles predicted solubilities as a function of temperature. So the reason that we need to do this is because of the many different polymers possible, there could be dozens to thousands of different solvents that we might have to assess to see whether or not the polymer is soluble. So we've generated a database at this point with 11 polymers and about 1,000 different solvents that have numerical values of our predicted solubility as a function of temperature. That's been published and is freely available as part of that citation. So what do we do with this solubility information? Well, here's how we'll design an example strap process. So let's say I want to take PE, EVOH, and PET as my 3 polymers that I'm thinking about. I can choose from my database solvents expected to be selective for each of these different polymers. What do I mean by selective? Well, here's an example of solubility as a function of temperature. So as this value increases, I can dissolve more and more of that target component. So this is why toluene is a great solvent for polyethylene. I can go to a high temperature and dissolve polyethylene while not dissolving the other 2 components. So I would choose this as a selective solvent that I might use to first take off the layer of polyethylene. If I want to get the polyethylene back out of solution, I can cool it, but it'll still have some residual solubility. I can also add acetone, which is what we call this anti-solvent, and I see the solubility crashes down to a very small amount. So this is an example of how I can then trigger the precipitation, or in other words, the recovery as a solid of my dissolved material. Okay, so we can do this with a whole bunch of different systems. Here's an example of what it looks like. We just took a physical mixture of these different polymers. We did strap, we chose solvents, we dissolved and reprecipitated. You can see we get out the isolated polymer components. PET is the last thing we try to dissolve, so we never dissolve it, and that's why it still comes out as these pellets. Once we've done the physical mixture, we take an actual multi-layer film. This is a commercial product provided by our collaborators. We do the same process, we get same yields. We've done a lot of characterization to show that the polymers are coming out in a chemically pure form. Okay, I am a chemical engineer, which means we show lots of what are called process flow diagrams with arrows pointing to where different things go and different temperatures. This is now the process flow diagram for that slightly more complex material that has the ink in it. And we can see that as we choose different solvents, we heat them up, we cool them down, we can extract polyethylene, EVOH, we can pull off all that orange ink that was in the label, and then finally we get our isolated polyethylene terephthalate, okay? Now, this ink is an example we'll call contaminant, okay? And I'll come back to that in just a minute. All right, so this all works well at lab scale. Just by that, I mean that, this is roughly the size of these. So we're talking about 40 grams of material. So how do we actually test that this works? Well, we've been working very closely with a company called Amcor. They're one of the world's largest plastic packaging manufacturers. They're conveniently located about 2 hours away from UW-Madison. And they're very willing to take our material, put them back into their production line, and test the quality of the films that are coming out using the material that we've generated. And so here's the first challenge where contamination plays a real role. So here's the polyethylene that we recovered from that solvent-based process. We dry it out. You'll notice that it looks very nice and white, exactly how we want it to be. We send it through an extruder. So basically, we make it into this rope-like material that is then what's used to produce the final film. And you can see a color change, okay? And that color change persists into the production of this film at Amcor. So this is really the material. Now, this color change is a really big issue, right? We can't sell this because it clearly has a property that isn't as good as the virgin material. We did a lot of work to show that this was the result of contamination. Specifically, some of the pigment that was used to introduce the color into that ink persisted through our process and ended up in the final material. So now we've gone back to the drawing board and we've introduced alternative processes. I'm not going to go through the details of what they are, but they allow us to remove more and more of that pigment and make our materials optically much, much more clear, okay? So this is an example of 3 different films, and hopefully what you can see is that as you go from sort of iteration 1 up to iteration 3, you can visibly see that this becomes less yellow. We can also quantify that. So here's just example optical properties, and I'm focusing on optical properties because they're easy to see. We've also tested other types of properties, mechanical properties, for example. And if I look at 2 control films in terms of clarity and haze, so if I can sort of see clearly through these materials, our 3rd generation of our strap process starts to lead to values very similar to the original control virgin materials. And indeed, if we look at metrics for color, we're going to the bottom right is desirable because our material becomes less yellow and more optically clear. Our new strap materials are getting very close to the virgin control. And this is actually not quite up to date. We've actually got it even closer by adding another unit operation. Okay, so we're generating materials that come from post-industrial waste, generate us plastics that are reusable as films, and are, we've heard, anecdotally now from Amcor that this is higher quality than what you typically get of mechanical recycling. It comes out in a cleaner form. Okay, so is this economically viable? Well, a lot of the work that we do in CUWP and in the center focuses on what's called techno-economic analysis. So basically, once I've mapped out a process, I can estimate the costs associated with each step in that process. And of course, we get more and more information as we go up in scale, so we treat these as estimates. But we can start to estimate using our process model based on things like the solvent price, operating costs, how much it costs to buy equipment, how much are we paying the operators that will run the plant, and then the economies of scale as we increase the amount of material that we deal with. So just to give you a sense, if we start to deal with about 3,000 tons per year of our recycled material, which sounds like a lot, but is actually an insignificant amount, this could be supplied by even a single plant in Wisconsin. We can see that based on our economies of scale, we're getting down to about $2 a kilogram to produce recycled PE, which is competitive, but slightly more expensive than virgin PE. Of course, that comes down as our processing capacity goes up. If we do multiple different polymers, so now we have multiple solvent washes, we can do PE and EVOH, our cost goes up, but something like EVOH actually has a really high market value, which makes this potentially useful. So those are the things that we're talking about. Related to this techno-economic analysis, we can do life cycle assessment to gauge, again, things like energy usage in terms of climate change impacts, greenhouse gas emissions, water usage, et cetera. I'm not going to walk through all this data, but we did a comparison against the production of virgin polyethylene, and our estimates are that we can produce this with lower energy, again, because we're not going through the polymerization step, and we also make some assumptions about the feedstock availability. But the essential idea is that in our models, we find that this strap process can actually be much lower in terms of its environmental impact, in addition to being economically competitive. Okay, so these are all positive things. Now, let's get to the last topic, which is contamination, right? So as we start to move from post-industrial waste, which is, relatively clean material, it's coming out of a factory, right, to now the post-consumer waste that goes through these material recovery facilities, we have to be increasingly worried about contaminants that are introduced that were not intentionally added to the plastics. They weren't there like the pigments, which are there to add color. I like this diagram. This comes from a Greenpeace article. It just really shows how people think about some of the contaminants that are being introduced. And we're going to hear, I think, from the next speaker about some of the regulatory issues here. But just as an example, there's been a lot of new regulation about perfluorinated compounds, PFAS compounds, ending up in recycling. And the big challenge is a lot of these are coming from non-intentionally added sources. There is some fluorinated material that's used as processing aids in polymer production, but there's a lot of fluorinated material that's just in the environment. So, there's volatile PFAS compounds that are short chain. So how do we think about removing things like legacy chemicals, endocrine disrupting contaminants, things that would not allow our recycled material to actually be reused due to either regulatory concerns, health concerns, or other reasons? Well, because we're using the solvent wash, we are ideally situated to think about removing contaminants that can dissolve in target solvents. So this is an ongoing area of work. Let me just show you two methods that we're working on. One is this idea of leaching. So this is an established approach. This would be that I choose a solvent where I put it sort of near the solid phase polymer, and thermodynamics causes the partitioning of my desired contaminant out of the solid phase and into the liquid phase. And I think you'll hear about this from Dr. Kurzweiler a little bit later on. But we can also imagine a separate type of approach where we both do strap to dissolve target polymers, and while dissolving a target polymer, we also pull off target contaminants, right? So how could we actually think about this in terms of our modeling? Well, we have access to computational tools that allow us to rapidly predict the thermodynamics of these types of partitioning processes. All right, so there's no fugacity here, but we have a partition coefficient, which we can think of as the ratio between the concentration of a molecule in the solvent versus the concentration of the molecule in the solid. So here we're just showing some predictions where we look at a wide range of phthalate compounds. These are additives that are put in things like polyvinyl chloride to help with their properties. And we ask, what solvents could we use to remove entire classes of phthalates that might be present in these polymers? So we can estimate log P values computationally, and then we can go and test them by formulating these polymers with a specific amounts of phthalate compound. Here we took PVC, we extruded it with BBP, which is a very common phthalate. We run our strap experiments using conditions suggested by computational modeling. And the end result is that we can remove almost 90 to 100%, depending on the condition and the temperature, after a wash or two. Okay, so we're starting to develop the thermodynamic basis for contaminant removal. Now, I want to focus on, these are phthalates. We focused on phthalates first because this is a very common contaminant in any of these chlorinated polymers. And we know exactly where they're going to show up in terms of waste. But what about much more complicated contaminants? I mentioned PFAS. Well, the huge challenge with PFAS is the molecular variability that you can find. So the EPA has a really great database with about 15,000 PFAS compounds that are expected to be environmentally relevant. If I imagine 15,000 different PFAS compounds, thinking about their solubility in 1,000 solvents and different polymers, it's impossible to do this experimentally. So here we're trying to use machine learning approaches to cluster these PFAS compounds into more digestible size range of different types of PFASs based on their chemical functionality, and design strap processes to remove specific types. Just to show you an example, we can do a method called dimensionality reduction, where we can take about 13,000 PFAS compounds and based on their chemical structures, identify clear types of clusters of similar compounds. We've identified about 23, which now we can think of as a much smaller design space for us to target using our solvent removal approach. So again, this is an ongoing area of work, and I'm happy to talk about this a little bit more offline. So with my final two slides here, I just want to emphasize that a lot of what we've been showing is at lab scale, but we're in an unusual situation where we're actually scaling up this process by building a pilot plant on a university campus. And specifically, we're working with Professor Ezra Barzib at Michigan Technical University to build a pilot scale plant for STRAP to sort of think about all the different issues we haven't thought about. Like, if we want to do continuous operation, we have to move polymer and plastic around. We have to dissolve it over a certain time scale. We have to worry about heat transfer. All of that are things that we can address at the pilot scale. And so the idea is for this to come into operation within the next year, where we can start doing 25 kilograms per hour of material and really seeing the feasibility of STRAP as we continue to move towards commercialization. So I'll end there by just saying that STRAP is our material, our physical dissolution method to target misplastous waste. Again, we think this can go alongside things like the advanced recycling technologies discussed by the last speaker, as well as alongside mechanical recycling. We think that it has great economic and life cycle metrics, and that we're really excited to continue working on getting this up to scale. So this was obviously a team effort. I'm just a representative of a large number of people, including our center director, George Huber, a number of faculty, including Professor Kurzweiler, who I think you'll hear from shortly, and some very talented students. Here I'm just highlighting Ugo, Kevin, and Pan, as well as Dr. Aurora Munguia Lopez, who will be starting her faculty career at Buffalo. Actually, she just started about a month ago. So if you'd like to read more, please go to the CUWP website. We also have some digestible fact sheets targeted at a general audience. And at this point, I'll stop and thank you for your attention, and I'd be happy to answer any questions.
Thank you for providing a great study. And I want to ask about can we reuse the solvent after treatment? And how many solvents use to get rid of each layer?
Yeah, so both of those are great questions. So the first question is about solvent reuse. So when we go into that process model, solvent reuse is absolutely critical. If you don't reuse the solvent, then your economics are terrible and your life cycle assessments are also bad because you're continually throwing out solvent. And that isn't even, so yes, you have to reuse the solvent. Right now we have assumptions about how many times that can be done. But what we know for a fact is that as you go through this process, you are going to have impurities build up in that solvent over time that eventually will cause you to have to shut down your plant, clean out the solvent, either distill it or do some other high energy process. So a big question, and this is what we hope we can answer with the pilot scale, is how many times we can reuse the same solvent before we have to do a cleaning step. Okay, so great question, and one that we hope to have more quantitative data on as we get up to pilot scale. The second question about the number of solvents, I skipped over this very briefly. If we use more than one solvent in a particular polymer removal step, so let's say I do the good solvent followed by an anti-solvent. Now I have a solvent mixture, and that means that I have to separate those solvents from each other, okay? So unit operations or processes to separate solvents are, again, energy intensive and therefore expensive. So at this point, we are using one solvent per polymer, and in actual commercial operation, we probably would not do this process where we cyclically remove everything from a particular plastic film. That doesn't make much sense economically. Instead, we want to choose the one solvent that'll give us the highest yield of our most valuable product. Yep, but thank you for your questions.
On your slide number 21, you have strep A, B, and C.
Yeah.
You went through that very quickly. Can you explain what you meant by the drastic change of environmental benefit from A to B and to C?
Yeah, of course. Yeah. So actually, this nicely ties to what the last question was. So yeah, I didn't talk about this. Strap A is where we add an anti-solvent to introduce precipitation. So this means that I have both a good and a poor solvent to remove every polymer. So as a result, I get this massive increase in energy usage because I have to separate the two solvents from each other. This is exactly what I mentioned in the last speaker. So this was a killer for us. So originally we got really high yields because of the anti-solvent. The LCA said that that's a no-go. So that's when we started to do strap B. This is where we chose a new set of solvents where we induced precipitation solely by reducing the temperature. So now we have a single solvent, and it's essentially a temperature swing process. We heat up to dissolve, we cool down to precipitate. And that's what strap B is. Strap C is actually, we just do a different film. So this was just a comparison of if we had different films with different compositions, sort of what is the sensitivity to film composition, and we see that it's still less than virgin film production.
Dr. Van Lehn, thank you so much for your presentation, and hopefully you'll stick around for the panel discussion.
Absolutely. Thank you very much.
Fantastic.